Okay, have you ever really stopped to think about what everything around us is actually made of? I mean, down at the tiniest level. The
Right.
air, this device you're listening on, everything.
It's a fundamental question, isn't it? And for a long time, even brilliant minds like John Dalton pictured the atom as this tiny, indivisible ball.
Right, like the ultimate building block. But science didn't stop there.
Mm.
Our deep dive today is all about how we peered inside that tiny atom, finding a whole universe within.
It's a fascinating story. We're basically going to unpack the atom piece by piece and see how these pieces dictate everything we see and interact with.
And we'll follow that historical path of discovery, right? Seeing how scientists actually figured this stuff out.
Exactly, which is, I think, super valuable for really getting these core chemistry concepts. We're drawing from great sources like Chemistry, Atoms First, and related lecture materials.
Our mission here is to give you that shortcut clarity, maybe some surprising insights, but without getting bogged down in heavy jargon. We want you to walk away with a solid grasp of why atoms act the way they do.
So let's start with that basic idea. What is an atom, chemically speaking?
Okay, so the definition is something like the smallest bit of matter that still keeps the properties of that matter.
Yeah, that's the key part, retaining the properties. The analogy I like is Lego bricks. You can have a big pile, break it down to single bricks. Each one is still a Lego brick, right? But if you smash the brick, now it's just plastic bits. It's not a Lego anymore. An atom is like that single brick, the smallest piece that is still the element.
Got it. So Dalton thought that was the end of the line, indivisible. But then,
Well, science marches on. We found out atoms are divisible. And when you break them open, you get what we call subatomic particles.
and those particles, how they're arranged, that's what determines everything about the atom and therefore everything about matter.
Precisely. So how did we start seeing these invisible pieces? That takes us back to the late 1800s, a time of intense focus on radiation.
The cathode ray tube experiments.
Uh,
Right, these evacuated glass tubes with metal plates.
yeah, connect to high voltage, and the negative plate, the cathode, shoots out this invisible ray towards the positive plate, the anode.
And it glowed when it hit a special screen at the end so they could see its path.
Right. And the really weird thing, it didn't matter what metal they used for the cathode. The rays behaved the same way.
So whatever these rays were made of, it had to be something fundamental, something inside all matter.
Exactly. Which leads us to J.J. Thomson. What did he figure out?
Well, he saw these rays were pushed away by a negative charge and pulled towards a positive one. Classic opposites attract, likes repel.
So he concluded they weren't rays at all, but streams of tiny negatively charged particles, and he called them
Electrons. But the genius part wasn't just naming them, it was measuring that charge-to-mass ratio.
Yes. He found this ratio was constant, always 1.76 times 10 to the 8th coulombs per gram, no matter the source. That was the light bulb moment. These electrons weren't just in some atoms, they were universal.
Incredible. But that's just a ratio. How did they pin down the actual charge or mass of something so tiny?
They required another piece of brilliance. R.A. Millikan and his oil drop experiment. Super clever setup.
Right, he managed to suspend these tiny charged oil drops and precisely measure the charge on them.
And he found the charge always came in multiples of one fundamental value. Negative 1.6022 times 10 to the minus 19th coulombs. That's the charge of a single electron.
Okay, so now we have the charge. And Thomson gave us the charge-to-mass ratio.
So you just do the math. Divide the charge Millikan found by Thomson's ratio, and bam, you get the electron's mass. An unbelievably small 9.0 times 10 to the minus 28th grams.
It's just amazing what you can figure out indirectly with smart experiments. Okay, so the electron is discovered. But things were getting even weirder, right? Other radiation was popping up.
Yeah, around the same time, Wilhelm Röntgen stumbled onto X-rays. These were different, not bent by magnetic or electric fields. So, no charge.
And then Becquerel's discovery. Radioactivity. Just spontaneous emission of energy from stuff like uranium.
Totally accidental initially. He found this radiation could expose photographic plates, even in the dark.
So what was this radioactivity made of?
Turned out to be three main types. Alpha rays, which were positively charged particles. Beta rays, which were actually just high-speed electrons, so negatively charged.
And gamma rays. High energy, like X-rays, no charge, not affected by fields.
Right, so now we know atoms have negative electrons, but atoms themselves are neutral overall, so there must be some positive charge in there somewhere to balance it out.
Which led J.J. Thomson, Mr. Electron himself, to propose the plum pudding model.
Oh, yeah. His idea was this sort of diffuse cloud of positive charge with the tiny negative electrons scattered throughout, like plums or raisins in a pudding.
It makes a kind of intuitive sense, I guess. Spread the charge out.
It was the leading idea for a bit, until one of Thomson's own students, Ernest Rutherford, decided to test it with his famous gold foil experiment.
Ah, this is a classic. So if plum pudding was right, what should have happened when Rutherford shot alpha particles at the gold foil?
Well, alpha particles are relatively heavy and positively charged. The gold foil was super thin, just a few atoms thick. If the positive charge in the gold atoms was spread out like in the pudding model,
Then the alpha particles should have just punched right through, maybe getting nudged slightly off course, but nothing dramatic, like shooting bullets through fog.
exactly. But that is not what Rutherford saw.
No. Most did go straight through, yeah. But some were deflected at pretty large angles.
And this was the stunner. A tiny fraction, like 1 in 8,000, bounced almost straight back.
Rutherford's famous quote, right? It was as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
It completely demolished the plum pudding model. There was no way a diffuse positive charge could repel an alpha particle that strongly.
So what was Rutherford's conclusion?
He deduced that most of the atom must be empty space. That's why most particles flew straight through. But there had to be a tiny, incredibly dense, positively charged center that contained almost all the mass.
The nucleus.
The nucleus. And the scale difference is just staggering. If the atom were the size of a huge sports stadium, the nucleus would be like a marble sitting in the center.
Wow. So typical atomic radius, maybe 100 picometers. Nuclear radius, like 5,000ths of a picometer.
Yeah.
Mostly empty space.
And within that tiny, dense nucleus are the positively charged particles needed to balance the electrons. We call those protons.
Okay, progress. Electrons orbiting, protons in the nucleus. We done? Does that explain everything?
Almost, but not quite. There was still a problem with mass. Take hydrogen, it has 1 proton. Helium has 2 protons.
So helium should be about twice as heavy as hydrogen.
Should be, based on protons alone. But experimentally, helium is about 4 times heavier. The math didn't add up. Something else had to be in the nucleus, adding mass, but no charge.
Ah, the missing piece. Took a while to find it, didn't it?
It did. Until 1932, when James Chadwick finally identified the neutron, an electrically neutral particle sitting in the nucleus right alongside the protons, with a mass very similar to a proton's.
And that explained the mass discrepancies. Helium has 2 protons and 2 neutrons, making its mass roughly 4 times that of hydrogen's single proton.
Precisely. So, quick recap. Tiny negative electrons in the vast space outside the nucleus. Positive protons and neutral neutrons packed tightly inside that minuscule nucleus. Those are our 3 fundamental subatomic particles.
Okay, so with those building blocks, we can now start defining specific atoms, specific elements. How do we do that? What gives an atom its identity?
It all comes down to the protons. The number of protons in an atom's nucleus is called its atomic number, and we give it the symbol Z.
And that number Z is the element's unique fingerprint, right? Like anything with 6 protons is carbon, anything with 7 protons is nitrogen, period.
Absolutely. It defines the element. And in a neutral atom, since the overall charge has to be 0, the number of electrons must equal the number of protons. So Z also tells you the number of electrons in a neutral atom.
Got it. Then there's the mass number, symbol A.
Yeah.
What's that?
Mass number A is simply the total count of particles in the nucleus. So the number of protons plus the number of neutrons. We sometimes call protons and neutrons collectively nucleons.
Okay, so if you know A, the total in the nucleus, and Z, just the protons, you can figure out the number of neutrons easily.
Yep. Number of neutrons is just A minus Z. So for example, fluorine 19, we look it up. Fluorine is element 9, so Zl 9 protons. The mass number is 19. So 19 minus 9 means it has 10 neutrons.
Makes sense. But this leads to an interesting point. If the number of protons, Z, defines the element, can atoms of the same element have different numbers of neutrons?
They certainly can, and that's exactly what isotopes are. Atoms of the same element, meaning they have the same number of protons, the same Z, but they have different numbers of neutrons and therefore different mass numbers, A.
Ah, okay. Like hydrogen, for instance. Normal hydrogen, called protium, is just 1 proton, 0 neutrons, mass number 1.
Right, but there's deuterium, which has 1 proton and 1 neutron.
Yeah.
Still hydrogen's Z1, but its mass number A is 2.
And tritium, even rarer, 1 proton, 2 neutrons. Still hydrogen, but mass number 3.
Or think about uranium. Uranium-235 and uranium-238 are both uranium Z92, but they have different numbers of neutrons, 143 versus 146.
Does having different numbers of neutrons change how they behave chemically?
Generally, not much. Chemical behavior is mostly dictated by the electrons and protons, so isotopes of the same element react very similarly. Their masses are different, which can matter in some physical processes, but chemically, they're almost identical.
Okay, let's talk about that nucleus again. All those positive protons crammed together. You mentioned repulsion. Why doesn't it just fly apart? And why are some nuclei stable forever, while others, like uranium, are radioactive and break down?
That's a deep question. It involves the interplay between the electromagnetic force, the repulsion between like-charged protons, and another fundamental force called the strong nuclear
The
force.
strong force. That's the one that holds quarks together inside protons and neutrons, right?
It is, and it also acts between protons and neutrons themselves. It's
Sure.
incredibly powerful, but only over very short distances, essentially within the nucleus. It's an attractive force between nucleons.
So it's a tug of war, proton repulsion trying to push the nucleus apart, strong force attraction trying to hold it together.
Yeah.
Stability depends on who wins.
Exactly. And the balance often hinges on the neutron-to-proton ratio, NP. For lighter elements up to about calcium, Z20, the most stable nuclei have roughly equal numbers of protons and neutrons, an NP ratio close to 1.
Okay, balanced forces. But what about heavier elements?
As you get more protons, the total repulsion increases significantly. To counteract that, you need proportionally more neutrons to add extra strong force glue without adding more repulsion. So for heavy of stable elements, the NP ratio gradually increases, climbing towards maybe 1.5.
More neutrons needed for stability as the nucleus gets bigger. Are there other factors?
Yes, some interesting patterns. Nuclei with certain specific numbers of protons or neutrons 2, 8, 20, 50, 82, or 126 tend to be particularly stable. We call these magic numbers, kind of like stable electron shells, but for the nucleus.
Huh, that's cool, like nuclear energy levels being filled.
Kind of, yeah. Also, nuclei with even numbers of both protons and neutrons are generally more stable than those with odd numbers of either.
And there's a hard limit, right?
Pretty much. Every known isotope of every element heavier than bismuth, Z83, is radioactive. They're just too big and proton heavy for the strong force to hold them together indefinitely. Plus, elements 43, technetium, and 61, promethium, have no stable isotopes at all.
Understanding this stability is crucial, isn't it? It connects to radioactivity, nuclear energy, even medical imaging.
Absolutely. Predicting which isotopes are stable and which will decay and how they'll decay is fundamental to so many technologies. It's really about understanding those forces at the heart of matter.
Okay, shifting gears slightly. When we look at the periodic table, we see an atomic mass listed for each element, like carbon is 12.01. But we just said carbon has isotopes, like carbon-12 and carbon-13. So where does 12.01 come from?
Great question. That number on the periodic table isn't the mass of just one specific isotope, it's the average atomic mass.
An average,
Yeah.
weighted by how common each isotope is.
Precisely. First, we need a standard. We define one atomic mass unit, AMU, as exactly 112th the mass of a single carbon-12 atom. So carbon-12, by definition, has a mass of exactly 12 AMU.
Okay.
Then we look at the natural abundance of carbon isotopes on Earth. It turns out that about 98.93% of carbon is carbon-12, and about 1.07% is carbon-13. Carbon-14 is radioactive and present in tiny traces.
So you take the mass of carbon-12, 12 AMU times its abundance, 0.9893, add the mass of carbon-13, about 13.003 AMU times its abundance,
Yeah.
0.0107.
And you calculate that weighted average. It comes out to 12.01 MU. That's the value you see on the periodic table. It reflects the average mass of a carbon atom you'd encounter in a typical sample.
How do we measure those abundances so accurately?
We use a technique called mass spectrometry. It's an amazing instrument that can essentially sort atoms or molecules by their mass-to-charge ratio, allowing us to determine not only the masses of different isotopes, but also their relative amounts very precisely.
That's how we know the exact percentages.
Cool.
Okay, so we've dissected the atom, talked isotopes, mass.
Oh.
Now let's zoom out to the big picture. The periodic table. It's more than just a chart, right?
Oh, absolutely. The periodic table is arguably the single most important tool in chemistry. It organizes all the known elements based on their properties in a way that reveals incredible patterns and predictive power.
So how's it arranged? We've got rows and columns.
The horizontal rows are called periods. Elements are arranged in order of increasing atomic number Z as you go across a period.
And the vertical columns are groups. What's special about the groups?
Elements within the same group tend to have very similar chemical and physical properties. It's like they're part of the same chemical family behaving in predictable ways.
That's the power of it. Knowing an element's position tells you a lot about how it might react. We also broadly categorize elements, right?
Yeah, into three main types. The vast majority are metals, usually shiny, good conductors of heat and electricity, malleable. Think iron, copper, gold.
Then on the upper right, you have the nonmetals, generally poor conductors, often gases or brittle solids, like oxygen, nitrogen, chlorine, carbon.
And straddling the line between them are the metalloids, or semimetals, like silicon and germanium. They have properties intermediate between metals and nonmetals, which makes them super important for semiconductors.
And some of those groups have special family names, don't they?
They do, and chemists use them all the time. Group 1A on the far left, except hydrogen, are the alkali metals, very reactive metals like lithium, sodium, potassium.
Group 2A next door are the alkaline earth metals, calcium, magnesium, also quite reactive.
Jump over towards the right. Group 7A are the halogens, fluorine, chlorine, bromine, highly reactive nonmetals. Group 8A are the noble gases, helium, neon, argon, famously unreactive or inert.
What about that big block in the middle?
Those are the transition elements, or transition metals. Groups 1B and 3B through 8B. Lots of familiar metals like iron, copper, nickel, zinc are in there.
Okay, so we have this amazing organizational tool. We understand atoms, but how do we actually work with them? They're ridiculously tiny. You can't count individual atoms for an experiment.
Exactly. If you have even a tiny visible speck of dust, you're dealing with billions upon billions of atoms. Counting is impossible. So chemists needed a way to connect the microscopic world of atoms to the macroscopic world we can measure, like mass and grams.
Enter the mole.
Enter the mole. It's the chemist's equivalent of a dozen, but for atoms or molecules. It's a specific number of things.
Like buying nails by weight instead of counting them one by one. The mole lets us weigh atoms to count them.
That's a perfect analogy. Officially, 1 mole is defined as the amount of substance that contains as many elementary entities, like atoms or molecules, as there are atoms in exactly 12 grams of carbon-12.
And that magic number, the number of entities in 1 mole, has a name.
Avogadro's number, Na. And it's experimentally determined to be enormous. 6.022 times 10 to the 23rd power.
602 sextillion. It's just mind-bendingly huge.
It really is. 1 mole of helium atoms, 6.02 by 10 sound of them, would fill a balloon a bit bigger than a basketball. It gives you a sense of how tiny atoms truly are.
So how does the mole connect to the mass we can actually weigh on a balance?
Through molar mass. The molar mass symbol is defined as the mass in grams of 1 mole of a substance.
And here's the beautiful connection. The molar mass of an element in grams per mole, mole, is numerically equal to its average atomic mass in atomic mass units.
AMU, exactly. So carbon's average atomic mass is 12.01 AMU. That means 1 mole of carbon atoms has a mass of 12.01 grams. Its molar mass is 12.01 gamol.
That's incredibly convenient. The number from the periodic table serves two purposes: average atomic mass in AMU and molar mass in gamma.
It's the bridge. Molar mass lets us convert between the mass of a sample, which we can measure, and the number of moles, which represents a specific number of atoms.
So the pathway is measure mass in grams, use molar mass, GOLO, to find moles, and then use Avogadro's number, atoms, to find the actual number of atoms.
Precisely. Mass molemoles number of atoms. That's a fundamental conversion pathway in all of chemistry.
And thinking about Avogadro's number really puts things into perspective, like environmental issues. You mentioned plastic bottles.
Yeah, think about it. Even a tiny fragment of plastic contains an astronomical number of large polymer molecules. That sheer quantity is why plastic pollution is such a persistent problem. Even microscopic pieces represent quadrillions of molecules that take centuries or millennia to break down fully. It highlights the scale we're dealing with.
It really does. So wrapping up this part of our dive, we've gone from Dalton's simple sphere to electrons, protons, neutrons. We've seen how atomic number defines an element, how isotopes add variety, and how nuclear stability works.
We've explored the elegant organization of the periodic table and, crucially, introduced the mole and molar mass as the tools chemists use to count atoms by weighing them. These are the absolute foundations.
You really now have a much deeper feel for the building blocks of everything and the clever detective work science used to uncover it all.
And hopefully you have the tools to think about the world from the incredibly small to the macroscopic on an atomic level.
So here's a final thought to chew on. We talked about the nucleus being incredibly dense, like 9 trillion times denser than iridium, the densest known element. Imagine if you could compress the entire Earth down to that same nuclear density. How big would it be?
It would shrink down to roughly the size of a football stadium.
Just think about that. The entire planet squeezed into a stadium.
Mm-hmm.
What does that kind of extreme density tell us about the fundamental nature of matter itself, especially when we look out into the cosmos at things like neutron stars or black holes? It really makes you wonder about the limits of matter and energy.